All right, let's dive in. Over the next few minutes, we're going to build your foundational toolkit for working with vectors. We'll break down the 3 most important operations that are literally the engine behind things like game physics and GPS. That's addition, subtraction, and scalar multiplication. Let's get to it.
You ever stop and think about that? I mean, how does a game engine know exactly where your character needs to land after a jump? Or how does your GPS reroute you in a split second? It seems unbelievably complex, but the answer, well, it starts with something surprisingly simple.
That's it. All of that amazing technology is built on the bedrock of vector math. And today, we're going to get a handle on those core ideas. So, first things first, what even is a vector? You've probably heard the word thrown around, but it's way more than just a number on a page. This is the absolute key. See, a normal number, what we call a scalar, just has a size, a magnitude. But a vector has both a magnitude and a direction. Think of it like this. Saying 60 miles per hour is a scalar, but saying 60 miles per hour north, now that's a vector. It tells you how fast and, just as importantly, which way you're going. And that's why they're literally everywhere. From a physicist calculating forces, to an engineer designing a bridge, to the graphics card rendering your favorite game, vectors are the language they all use to describe things that have both strength and direction. They are an absolutely essential tool. To make all this feel a little less abstract, we're going to get to know 2 specific vectors and follow them through our 3 operations. You can think of them as the stars of our show. And here they are. We've got vector A, which is our blue one. It goes 2 units over on the x-axis and 3 units up on the y-axis. Then we have vector B in red. It goes 1 unit over on the x-axis and 1 unit times down on the y-axis. So keep these 2 in your head. We're going to be seeing a lot of them. First up, addition. You know, if you have 2 different forces pushing on an object, how do you figure out the final combined force? Well, you add their vectors. And the best way to really wrap your head around this is with a super intuitive visual trick called the head-to-tail method. Okay, so this is how it works. It's really a simple 3-step process. First, you draw your first vector, vector A, starting from the center, the origin. Second, you take your next vector B and you place its starting point, its tail, right at the end point or the head of vector A. And finally, the answer, what we call the resultant vector, is just a new arrow you draw from the very beginning of A all the way to the very end of B. That's it. It shows you the total result of those 2 movements combined. Drawing it out is awesome for building that intuition, but how do we calculate the exact answer? Well, the good news is the math is just as simple, and you'll see it lines up perfectly with the picture we just drew. It's honestly this direct. You just add the matching parts together. The I represents the x direction and the j represents the y direction. So we add the I parts, that's 2 plus 1, which gives us 3i. Then we add the j parts, 3 plus -1, which gives us 2j. So our final answer is 3i plus 2j. The math confirms exactly what we saw visually. Okay, let's move on to subtraction. This might seem like a whole new ballgame, but there's a really clever trick to thinking about it that makes it, well, it makes it basically the same as addition. This is the whole secret right here. Instead of trying to learn a whole new set of rules for subtraction, we just turn it into an addition problem. A minus b is the exact same thing as a plus the negative of b. So what on earth is a negative vector? It's really simple. A negative vector has the exact same length, the same magnitude, as the original. It just points in the complete opposite direction. So if our vector b was 1i minus 1j, then negative b is negative 1i plus 1j. We just flip the signs on each component. It's the same arrow, just spun 180 degrees around. So now we can solve a minus b just like an addition problem. We take the x components, 2 minus 1, that gives us 1. For the y components, we have 3 minus -1. And hey, be careful with that double negative there. That becomes 3 plus 1, which is 4. So our final answer is 1i plus 4j. See? Simple. All right, last but not least in our toolkit, scalar multiplication. This one isn't about combining 2 vectors. It's about taking one vector and just resizing it. Like, what if you wanted to double a force or cut a velocity in half? This is the whole idea. When you multiply a vector by a regular number, a scalar, you're just stretching or shrinking it. If you multiply by 2, the vector becomes twice as long. If you multiply by 0.5, it becomes half as long. But, and this is crucial, its direction doesn't change one bit. Let's see this in action really quick. We're going to take our blue vector A and we're going to multiply it by the scalar 2. And the calculation is a piece of cake. You just distribute that scalar to each component inside. So we multiply 2 by the 2i to get 4i, and we multiply 2 by the 3j to get 6j. Our new vector is 4i plus 6j. It points in the exact same direction as our original A, but it's now twice as long. And there we have it. Those are the 3 fundamental operations that are the building blocks for so much. Let's do a quick recap of the main ideas, just to make sure they stick. So just remember, for addition, think head to tail. For subtraction, don't even think subtraction, just add the opposite. For scalar multiplication, you're just resizing. And maybe the biggest takeaway of all, always try to picture the arrows. Understanding the geometry behind the numbers is what really gives vectors their power. With this toolkit, you now get the fundamental language of motion, of forces, of computer graphics. So the next time your GPS recalculates your route, or a character in a game lands a perfect jump, you'll know that it's all being powered by these simple, elegant rules we just covered. It makes you wonder, what else around you is being guided by this math?